In this video we're going to examine convection generated due to surface heating. So after sunrise the Earth's surface is heated by solar radiation, and that shortwave flux warms up the Earth's surface much more efficiently than it does the free atmosphere. And so the heating that occurs in the Earth's surface needs to be spread to adjacent layers of the atmosphere by different mechanisms. The first is molecular conduction, and that works for the layer of atmosphere that's immediately adjacent to the ground, so it's in thermal contact, and that's a layer of several centimetres deep. Then you have turbulence, so eddies mix warm air from near the surface upwards to greater depths, and it brings down cooler parcels of air to lower levels, and so you mix up the layer of atmosphere near the surface. And then there's convection. Strong heating can produce a super adiabatic lapse rate near the surface, and that results in vigorous convection, which transports heat upwards. So surface heating and convective mixing create a dry adiabatic lapse rate from the surface, which gradually extends higher and higher up in the atmosphere. We can actually have a look at this. So on the right hand side is a figure which illustrates the depth of what's known as the mixed layer depth, or the boundary layer, and it's the depth through which turbulent mixing is occurring. So you notice it's very shallow early on, and then the depth increases fairly rapidly initially, because very often you'll start with a temperature inversion, a radiation temperature inversion, and that can mix out fairly rapidly. The greater and greater the depth of the mixed layer becomes, the slower and the slower the heating is over time, and so you can see that the height of the mixed layer asymptotes as you move into the afternoon. It becomes you end up with a greater depth of atmosphere that you're dumping energy into, and so it takes longer and longer to increase the temperature of that deepening layer. Now as this occurs, if a lifting condensation level or a level free convection is reached, then you'll get convective cloud forming. But if no cloud forms, then you have what's known as dry convective mixing. And this can be a turbulence hazard in summer because it can actually be really quite vigorous. In inland Australia, that can reach to a depth of 500 hectopascals, so 18,500 feet, over which this dry mixing is occurring. As noted before, what happens with this heating and thermal mixing is the establishment of a dry adiabatic lapse rate. And here's a profile where there's a radiation inversion, so this is 11 UTC trace. In summer that's 10 PM. And then there's a very deep dry adiabatic layer from pretty much near the surface to 700 hectopascals, which is about 10,000 feet or 3 kilometres. You can see that lower down there's also a well-mixed dew point profile, which approximates an isopleth of a mixing ratio. Here's a question for you. During convective mixing, how will the 10-metre wind speed change from the radiation inversion conditions early on AM to well-mixed conditions in the afternoon? Pause the video and discuss this with your colleagues. So what did you come up with? The answer actually depends upon where you are. In the mid-latitudes in the morning, the radiation inversion means that there's a decoupling of parcels near the surface with those further aloft. So if there's an inversion, it means that parcels that are lifted have a negative buoyancy, so they come back down. So you cut off what happens at the surface with what happens aloft, and of course near the surface you have friction. So overnight and early morning, typically, all other things being equal, the wind speed reaches a minimum. And then when thermal mixing breaks through that inversion, the wind speed should pick up. But particularly in the tropics, where that mixing is very, very deep, you're actually mixing out a lot of momentum. And so you get an afternoon minimum in the winds with a morning maximum. So that's an important difference to note, particularly if you end up doing fire weather forecasting, that the morning winds in the mid-latitude will be weaker than the afternoon because you break through a radiation inversion due to the thermal mixing and bring down higher momentum air from aloft. Whereas in the tropics, what happens is that you mix through such a great depth, the total momentum in the layer decreases, and so the wind speed decreases in the afternoon. Let's look at convection due to surface heating now, and here we have a dew point profile and a temperature profile. You can see at 6 AM there's a radiation inversion. we can perform our equal area method in the lowest 50 hectopascals to get the mean mixing ratio that will represent what convective parcels do. And then, as the surface is heated by shortwave radiation, we establish a dry adiabatic lapse rate below the inversion. So the inversion starts to be eroded. And then by 10 AM, we're close to the top of our inversion. And by 12 AM, we have the convective temperature. So that's the temperature combined with the mean mixing ratio that provides us with a level of free convection. And then, of course, during the afternoon, so there's our convective condensation level, which is a level of free convection. And so convection first starts at the convective temperature. But of course, I keep jumping ahead of myself. Here's the saturated adiabat up which parcels will ascend. But then, yep, here we go finally. The temperature of the surface continues to rise, and so the cloud base will continue to rise during the day. So what happens to the equilibrium level with that increased warming? Well, we expect that the equilibrium level will also rise as the parcels of air move along a different saturated adiabat, which is to the right of the one represents the convective temperature, and so they'll intersect the tropopause at a slightly higher elevation. You can see too that as we get more and more warming during the day, the temperature, or more particularly the virtual temperature difference between cloud parcels in the environment, will increase, and so we get more and more CAPE realised. Although we do lose some depth of cloud because the convective condensation level lifts, but typically speaking, it'll still represent an increase in the CAPE. So we arrive at something known as the convective temperature, which we saw as the temperature that we surface convection is first initiated, and that corresponds to a convection condensation level, the height to which a parcel of near surface air, if heated sufficiently, will rise adiabatically until it is just saturated. And if the surface temperature is equal to Tc, the convective temperature, then the convective condensation level is equal to the lifting condensation level is equal to the level of free convection, and parcels will therefore freely convect. That is, they're ascending due to the release of latent heat. You used this trace in an earlier exercise in another video. So for this trace, determine the mean ARF, the lowest 50 hectopascals, the convective temperature, and the convective condensation level in hectopascals and feet using the ICAO atmosphere. Determine also the level of free convection and lifting condensation level at the time of sounding, that is the morning time, in hectopascals and feet. And finally ask, what happens to the lifting condensation level and the level of free convection if the surface temperature reaches the convective temperature? Pause the video now and carry out this exercise. So how did you go? If you use the lowest 50 hectopascal mixing, you get a mixing ratio of about 14.7 grams per kilogram and a convective temperature of about 36 degrees, which gives you a convective condensation level of 800 hectopascals or 6,500 feet. You can see that the lifting condensation level is much lower than that, at about 5,800 feet, and the level of free convection for that lifted parcel is at about 8,000 feet. So there's quite a bit of convective inhibition to overcome, a lot of lifting to do. Of course, as we noted earlier, if the surface temperature reaches the convective temperature, then the LCL is equal to the LFC is equal to the CCL. And that's most likely the way in which convection will occur for this environment. Now, this is a Darwin trace, and the METAR is given there, and you can see that for 34.3, which is close to but not precisely the convective temperature that we worked out, observed was broken cloud at 6,300 feet, which is about the CCL. There are, of course, some discrepancies with what you've calculated. And the trace can vary quite a bit from place to place and in time. So you can launch a balloon separated by as little as a few minutes, and you'll find that the environment will have varied slightly. And so the whole key behind forecasting deep convection is to consider the worst case scenario. Finally, also consider convective and stratiform cloud together with things like the wet bulb process, but also if you've got some level of lifting between a level of free convection and a condensation level, the cloud between those two layers will be stratiform cloud.